Hi, this is John Gardner, Mechanical Engineering Professor at Boise State University, and we have another video here of our series on industrial refrigeration systems. This is I'm pretty sure it's going to be the final one in the series, at least for this year, and we're going to talk about how to analyze condenser operation and system operation in light of weather changes and weather patterns in a given year. So we're looking at a yearly and annual kind of analysis, and this is going to show you how to adapt it from one location to another. So we talked about the wet bulb temperature, which is a function of the dry bulb temperature, the normal temperature, and the relative humidity. It changes through the course of a day. And evaporative condensers create a microclimate, an environment inside the condenser that is essentially driven towards the wet bulb temperature. In an efficient system, so it's operating well, it's set up so that the condensing temperature and pressure floats above the wet bulb temperature by 20 degrees or so, depending on how the system is designed. It's called a floating discharge pressure, or floating head is another thing they refer to that. So to get an idea of how this might operate, to estimate the cost of this operation, we have to see how the wet bulb temperature varies over the year for a given location. Fortunately, that data is available, though we have to manipulate it a little bit. We have these files called typical meteorological year files, TMY, and they're created and maintained by the National Renewable Energy Lab, one of the Department of Energy's national labs. Contain hourly data for a given location, and that includes humidity, temperature, solar energy coming in from all sorts of different ways to measure it, and it's done hour by hour, so it's 8,760 lines in it. It's built from real data, so it's not really averaged as such, but they look at 30 years worth of data, and they say, okay, for this location, which one of those 30 years has the January that was most typical? So the most kind of the average here, but they didn't get it by averaging all the data. They said, say January of 1987 was a very average year. So we'll use the data that we measured in that January and put it in the file. And then we do the same thing and look at February and so on. And so you build this up from real data. Now, if you take, a January from, say, 1980 and a February from 2003, you might have a discontinuity. So they do some smoothing over plus or minus a couple days as you transition across the months. But when you end up with is real weather data, and when it represents a typical year. You can find the files online. If you just search for TMY files, it'll take you right to this source at the National Renewable Energy Lab. I pulled up the one from Seattle. It's a CSV file, so Excel opens it up just fine. It's a lot of data. You can see here every line is an hour. The top line gives you an indication of where it is. So there's latitude and longitude up there, Seattle, Washington. Here you can see the January they used was 1987. Most of the data in the left-hand part, these first 20 or so columns, is various ways of measuring sunlight and insolation. But if you scroll to the right here, get up into the 30th column or so, you get the temperature. So dry bulb temperature is right here in column AF. Column I has the dew point temperature, and column AL has the relative humidity. So you see we've got relative humidity, we've got dew point, we've got dry bulb. The only thing we really want, though, is wet bulb. And unfortunately, the TMY file doesn't contain that. However, since thermodynamics tells us if we know any two states of that mixture, we can find all the other properties, then certainly with relative humidity and dry bulb, we can get dew point. We can get wet bulb, which is what we want. And indeed, we can. So here's a paper that was written in 2011 by Roland Stoll in Canada, and the Journal of Applied Meteorology and Climatology. And he gave us this formula. So the wet bulb temperature is a function of the dry bulb temperature and relative humidity, and a bunch of arctangents and a square root. So relative humidity is as an integer. So as they show here in the example, 65.8% means it's 65.8. So you go into that TMY file, open up a new column, program that formula in there, copy it down through the file, and now you have a column for wet bulb temperature. Once you have the wet bulb temperature, we can make a histogram, divide it up into cells, say, okay, for wet bulb between 30 and 35 Fahrenheit, how many hours in a year does that happen? Well, it turns out I've done that, done it just recently. So when we were in Kodiak, Alaska, we wanted to see what the we wanted to look at this very analysis. So I found the TMY file for Kodiak, put in that formula for the wet bulb, and found this distribution of wet bulb temperature. So for what, about almost 3,300 hours in a year, it's approaching half a year, that wet bulb temperature is really cold. It's right around freezing, 30 to 35 Fahrenheit. And certainly for the vast majority of the time, it's under 50 degrees Fahrenheit. So it's pretty chilly, as you might imagine, being that far north. So what does that mean for condenser operation? Well, we talked about the fact that if it's behaving well, it floats above that. So the lower the dew point, I'm sorry, I should get this right myself. The lower the wet bulb temperature, the lower the condensing pressure will be. And that's a good rule of thumb, except for the minimum. All systems have a minimum pressure. If it gets too low, they take action to make sure that it doesn't. And that usually has to do with the way the system's been designed and operates. So it could be hot gas defrost, or it could be the way the compressors are being cooled. If they use liquid injection, it's called, to cool it, then they can't get that pressure too low. But it's that pressure that's set, the minimum pressure setting, is what really determines energy efficiency. If they have it set too high, they're going to just waste a whole lot of energy. So let's go through this study, and I'll kind of walk you through what I did with this one Alaskan food processor. So the first thing you have to do is go through the thermodynamics, like we did for the intercooler homework, and do the thermodynamic analysis on a per unit mass of refrigerant basis. But in this case, in the homework, you change the intercooler pressure. In this case, change the condenser pressure. So go through this analysis of all the different states and find the amount of compressor work per unit mass of refrigerant as the condenser pressure or the discharge pressure changes. And you'll see it goes up as the pressure goes up. And in fact, here's the results I got. So I went through and did 5 different discharge pressures in absolute psia, and I looked at compressor horsepower per 100 tons of capacity. And obviously, if you want horsepower per ton, you just divide these by 100. And sure enough, it's a pretty straight line, obviously, and probably theoretically it probably is perfectly linear, but the small variation here is probably due to imperfect thermodynamic properties. We've talked about that. It's very sensitive to that, right? So we combined that results of our discharge pressure study with the weather data. So we find the number of hours it's likely to operate at each temperature range, add the approach. Don't worry about subfreezing because the minimum pressure setting is gonna take over anyway, and assume 24/7 production. And you've got enough information. So let's walk through that. So let's say you've got a system that's currently running at 160 psia. That's the minimum set point. The operator doesn't want to mess with this floating thing. He just has it cranked up all the way. It turns out it actually will likely spend some time higher than that, but not very often. And so I'm just going to assume it's constant at 160 psia because that's our baseline. I want to see how much lower it'll be if I change the minimum pressure. And in fact, that's what we want to do. So we want to say current thing is that the minimum pressure is 160 psi, or that it's constant at 160. I want to set a minimum of 120 to let it float around in between those two ranges. So here's our base case. So at 160 psia, we found that the horsepower requirements was 1.82 horsepower per ton. That was on that little graph a few slides back. Conversion between kilowatts and horsepower. I just assume 90% energy, 90% efficiency of the electric motor that drives the compressor, number of hours per year. And for every ton of refrigeration capacity, it requires 13,215 kilowatt hours in a year. Not surprising. So that's our baseline case. So if the average refrigeration load, and this is the factory can tell you on average what they run, is 500 tons, then we'd estimate we'd use 6,607,500 kilowatt hours over the course of a year. Okay, so so I want to, so that's the baseline. I think I wanted to move this. No, okay, sorry about that. Here's the table. So I want to set the minimum pressure, discharge pressure, to 120 psia. So what I have here are those same bins I had on the histogram from the modified TMY file. And then over here, jump over here, are the hours of operation. Again, that's right from the histogram. So that's part of what we're doing here. Now this is the temperature, the discharge temperature, assuming a 20-degree approach. So I just add 20 degrees to that. So 35 to 55, 40 to 60, 45 to 65. So the approach assumption creates this column by just adding the approach to the top end of our temperature range here. So that means the target discharge pressure is the saturation pressure associated with that. So you go into the ammonia table and say, oh, okay, what's the saturation pressure for 55? Well, it's 98 psia. What is it for 60? It's 108, and so on. So at all these different ranges of the wet bulb temperature, that is a discharge pressure that'll maintain the 20-degree approach. Well, remember, we're setting a minimum pressure, so it's 120. So any of these numbers that's lower than 120, you've got to turn them into 120. And so that's these first three cells. And then this is the horsepower per ton rating we got from the discharge study. So as you can see, we've got enough information here from the horsepower, hours of operation, to build up a case of how much energy it would use over the year. So I just took that same data, took the horsepower per ton, hours per year, added it together, and came up with a number that 11,502 kilowatt hours per ton of refrigeration in a year. Going back to our assumption of a 500-ton average load, the annual average is 5,751,000. Remember, the other one was 6,607,000. Quite a bit of savings, 156,000 kilowatt hours. If you're paying 10 cents a kilowatt hour, it's $85,000 a year just by changing a setting in your system. Sounds easy. It turns out that these things are incredibly finicky. And so what most operators do is they say, well, you know, the lower the pressure is, the more likely is something might go wrong. I just keep it high because, heck, I'm not paying the electric bill. And again, like I said, there's certain quirks in the system that may require it to be higher. As efficiency engineers, we're not trained refrigeration design engineers, but we can certainly have this discussion. Say, okay, what is it that's limiting you at your minimum pressure? And this sort of analysis can tell you how much money is at stake by running at a minimum pressure that's too high. Okay, so that's the information. So I've got now a homework assignment posted, which is to redo this analysis I just showed you. So use that same horsepower versus discharge pressure. So that same analysis I already did. You don't have to redo that. Assume a condenser approach at 20 degrees Fahrenheit. Assume a baseline discharge pressure of 150 psia instead of 160, so a little bit lower. And use the TMY file for your region. Okay, so in the printed homework, the PDF, it shows for the folks up north, use Spokane, Washington. For the ones down here, I suggest Twin Falls, Idaho, because that's where most of the food processing plants are. And so you'll have assuming, I think I've got the other information on there, but we're going to ask you for what's the energy savings if we set a lower minimum pressure. So that's it. Any questions, feel free to drop me a line. Thanks.